Hello everyone, I am Luis Alejandro Bernal Villalobos, and today we're going to solve uh, a point from the CRG exam from the year 2017, month of, month of May. This is problem type 1, equilibrium of gaseous reaction, and this is going to be a solution guide as a part for my master leadership class. As I said, this is going to be a preparation for the CRG exam in charge of Professor Schutz. So, okay, let's jump right into it. So the problem says toluene can be used for storage of hydrogen if the gas is bound to the molecule in chemical reaction to methyl cyclohexane. Here is the reaction. Your task is the determination of the equilibrium between toluene, hydrogen, and methyl cyclohexane at different temperatures in order to discuss the process conditions for storage and recovery. Assume the following temperature dependence of all heat capacities. So here is a table. What does this table says? Here is some polynomial values for the heat capacity for the CP, and the standard heat and not heat enthalpy of formation, and the standard entropy of formation of these reactants of these substances. So solution guideline. Point A. Calculate the reaction constant K at 298.15 Kelvin. So if we look at this Excel sheet, I took the liberty of typing some values. So let's see them one by one. So here we have some equations that were taken directly from Professor Schutz's notes. You can also find them in any thermodynamic book. And I'm not going to take time to describe how they were deduced. I'm just going to use them. So those are the questions that we are going to use. What do we have here? We have a temperature of reference, the temperature that it is asked to calculate this K value, and the constant R of ideal gases. What do we have here? We have the reaction coefficients for each substance. So if we look at this reaction, it says 1 mole of toluene plus 3 moles of hydrogen produces 1 mole of cyclohexane. So let's remember that for reactants, the stoichiometric coefficient is -1. Well, for toluene is -1, for hydrogen is -3, and for cyclohexane is 1, because it's a product, it's positive, and if it's a reactant, then it is negative. Here we have the reaction once again, so we don't forget it. Here we have all the substances, all the compounds that are treated in this problem. So what is asked? It is asked that we need to calculate the Kp value. So to do this, let's see at the Kp equation. To do that, we need to calculate the enthalpy and also the change of entropy. So we need to look at these equations to calculate that. So to calculate the change of enthalpy, we need the standard enthalpy of formation and some CP values. And for the entropy, we also need the standard enthalpy of formation and also CP values. So what we can do is by calculating the CP, the calorific capacity at this temperature at 298. So that is what we're going to do first. We're going to calculate the standard calorific capacity. And how are we going to do that? The exercise gave us this table in which the calorific capacity can be calculated as a polynomial. This one would be order 0, this one order 1, order 2, and order 3. So I just copy and pasted these values that are in this table here. So it's a little bit, or it's organized differently. This section would be for toluene as a reactant. This section would be for hydrogen, also as a reactant. And this section would be for cyclohexane as product. So let's begin by doing that. So we're going to calculate the standard calorific capacity at the standard, the reference temperature, that is 298.15 Kelvin. So as I said, it's going to be a polynomial. This would be order 0 plus this polynomial times the temperature plus this part of the polynomial times the temperature raised to the second power plus the third part of the polynomial times the temperature raised to the third power. So we can see here this would be the standard calorific capacity at 298.15 Kelvin for toluene. So let's do the same, but this time for cyclohexane, for one of the products. And this would be here. It's exactly the same equation. We just take each part of the polynomial, we multiply it for the temperature raised to 0, to 1, to 2, or to 3. So that's why I just copy and pasted the equation. And that would be 134 joules per mole Kelvin. And let's finish it for hydrogen. So I'm going to do it once again, so it's just clear. Is this plus CP1 times the temperature plus CP2 times the temperature raised to the second power plus CP3 times the temperature raised to the third power. Okay, and that would be the standard calorific capacity for hydrogen at 298.15 Kelvin. So what we're going to do next is we're going to do exactly the same thing, but this time we're not going to calculate it at the standard reference of temperature, but a temperature that we would like to enter in this program. In the first point, it is asked that we do it for 298 Kelvin, but next they're going to ask us to do it at different temperatures. So it would be the same equation that we used before. So yes, let's just copy and paste it so we can save some time. But the only thing that it's going to change is the temperature that it's evaluated. It's not going to be at the reference one, but at a temperature that we decide to. Okay, so that's nice. We do the same for the cyclohexane. And finally, we're going to do the same for the hydrogen. But it's not the reference temperature. Let's remember, it's the temperature that we as users define. In this case, it's the same. So let's stop right here. We can see that these values are the same for toluene, for cyclohexane, and for hydrogen because they are the same temperatures. So for example, let's change this temperature to see what happens. We can see that this value also changes. So that's why we did this. So we have two different CPs evaluated at different temperatures. That is going to be handy later. But we're going to leave it at 298.15 because that is the first point. So next, we're going to calculate the mean calorific capacity. If we see this equation for calculating the change of enthalpy, we need this integral of the CP that changes with respect to the temperature. And there are many ways to calculate this integral, but one that is pretty simple is just take the high value, then the low value, and just take a mean of those two values. But there are other ways to calculate this integral. One of them is using the traps equation function from MATLAB. I believe there also exists the Simpson rule. You can search for yourself how you can calculate this integral analytically. Even so, you can also integrate this equation with respect time. It's pretty simple because it's a polynomial, and you can compare these results. But in this case, I'm just going to use the mean value that it's acceptable. So it would be just the mean of the CP value evaluated at the reference temperature, that would be this one, and the CP value evaluated at the temperature that we decide as users, this one. And that would be exactly the same for the cyclohexane and hydrogen. And we can see here, as we have the same value of the CP, then the mean, it's also the same value. But let's change, for example, here to 400. We can see that this would be the mean of these two values. Okay, but just let's leave it as it was before. Okay, so we have now how to calculate the CP value in these equations. So let's start on calculating the standard change of enthalpy. If we see this equation, it says is the sum of the stoichiometric coefficients time the standard enthalpy of formation. So, sorry, I believe that I said that wrong before. We're going to calculate the standard enthalpy of reaction. And for that, to calculate the standard enthalpy of reaction, we need the standard enthalpy of formation, that it's here. I already copied it from the problem. It was given in this column. Be careful about the units. I already copied it. This would be for toluene, this one would be for cyclohexane, and this one would be for hydrogen. So let's remember that the standard enthalpy of formation of pure substances is 0. That's why it for hydrogen is 0. And yes, if in the exam you don't have these values, I would suggest to take them from the Smith book of thermodynamics, or also the Pauling book. Pauling has a really big database of values for pretty much anything that you can imagine of a substance. It's a pretty big database, so I would suggest you use the Pauling book or the Smith book for thermodynamics. But in this case, this data were given, so I just copied and pasted. So let's go back to the equation. It's the sum of the stoichiometric coefficient times the standard enthalpy formation. And what does that mean? This equation means that we need to multiply this stoichiometric coefficient with this standard enthalpy of formation. Then what we are going to add to that, this stoichiometric coefficient, we are going to multiply it with this standard enthalpy of formation, and that we are going to add this stoichiometric coefficient multiplied by this standard enthalpy of formation. That is what this sum means. Really important for this sum is the value of the stoichiometric coefficient, that it's negative for reactants and positive for products. So luckily, Excel has a predetermined function to do this kind of calculations that is called sum product. One disclaimer, my Excel is in Spanish, so you will need to find these functions in English, but I believe it's not that hard to find. So we're going to use the predetermined function sum product using this matrix and that the matrix of the reaction coefficients and the matrix of a standard enthalpy of formation. And there you have it. We have the standard enthalpy of reaction. So we already calculated this, and okay. It says here that okay, let's proceed with calculating the standard entropy of reaction, and it's very similar to this equation. Here we can see the standard entropy of reaction is just the sum of the stoichiometric coefficient multiplied the standard entropy of formation. So we're going to use once again the predetermined function of Excel, sum product, that can calculate this sum. We take the matrix of the reactant coefficients and the matrix of the standard entropy of formation. Once again, these values were taken from the guide, from the problem of the exam, but you can find them in any book of thermodynamics. A good one, I mean. And that would be the standard entropy of reaction. Okay, so we are close. We are almost halfway there. So now we are ready to calculate the change of enthalpy in the reaction and the change of entropy. Let's begin with the change of enthalpy. What would that be? We would say it would be the standard enthalpy plus the change of the calorific capacities. But as we discussed before, we can calculate this. A simplification of this integral would be just the mean. So what it is? It would be the standard enthalpy of reaction that we calculated before plus the sum product of the reaction coefficients, this part, and the mean of the mean calorific capacity that we calculated here. That's why it was important. And to that, we multiply the temperature at which it's evaluated minus the temperature of reference. And there you have it. We have there the change of enthalpy of the reaction. So let's calculate now the change of enthalpy of the reaction is pretty similar. It will be the standard one plus, if we can see here, it's once again the sum product of the stoichiometric coefficients that are right here and the mean. This CP is just the same as this one, is the mean calorific capacity. So this matrix. And to that, we are going to multiply this natural logarithm of the temperature, the temperature divided the reference temperature. And that would be the change of enthalpy of the reaction. So we are almost there. We can now do the final step to calculate the Kp equilibrium. So we see at this equation, we need to calculate this. It would be the exponential function of what? Of 1 over the gas constants. Be careful about the units here. Multiplied by the change of enthalpy of the reaction divided the temperature at which it was evaluated minus the change of entropy of the reaction. Okay, times -1 because it's negative. Okay, so there you have it. That would be the answer of point 1. So let's write it here. Point A, I mean, point A. So it would be Kp at 298.15 Kelvin. 198.15 Kelvin would be this value. So let's copy and paste it. As you can see, it's very big, but we're going to discuss that later. Okay, so that would be point A. So let's continue with point B. It says, repeat the calculation of the reaction constant K at 500 Kelvin and 600 Kelvin. So we need to, for point B, to do pretty much the same thing. Point B, but at 500 Kelvin and 600 Kelvin. So as you remember before, I suggested to calculate the calorific capacity also at the temperature T, just because of this. So we can do this point much more faster. So the only thing that we need to change in this sheet to obtain this Kp at 500 Kelvin is to change this temperature at 500, and there you have it. All the cells are changed. It's pretty handy, and now we have the new value of Kp at 500 Kelvin is 74, much more smaller than before. And we do the same, but at 600 Kelvin. And now the Kp is once again dramatically reduced. Is 0.015. Okay, that would be point B. Now we have 9 points right there. So let's continue with point C. Calculate the equilibrium partial pressures at 600 Kelvin at 1 bar, as well as the equilibrium at 500 Kelvin, 500 Kelvin and 50 bar total pressure, assuming in both cases a stoichiometric input of the reactants, and apply an iterative solution method solver. So okay, we're going to do point C. So we're going to do it first at 600 Kelvin. And it says that the total pressure would be 1 bar. 1 bar. So, okay, to solve this solver, there are many ways to solve these types of solver on how you can formulate the equations. But I found that this one is pretty handy because you almost force Excel to solve this problem, and it doesn't have too many degrees of freedom. Here, in this way that I'm going to formulate this problem, it's just going to have one variable. There are many ways you can formulate this problem with 2 or 3 variables, but only having one is much more easier for the solver to solve this problem. So okay, so what do we need? We're going to need the Kp value that we calculated in the last point. And what it is asked is that we need to calculate the partial pressures of each compound. So let's remember from this table that A is toluene, B is hydrogen, and C is cyclohexane. So we're going to have these are the partial pressures in bar. Let's not forget about that. In bar and in bar, and we are going to need the total pressure of the system, P total in bar. Okay, so let's start formulating the problem. Well, the Kp at 600 Kelvin we calculated from before. It's just this value, 0.15. And the problem says that we need to calculate these 3 partial pressures at P total, that would be 1 bar. The sum of so yes, here are the conditions that we need to meet. First of all, what we are going to do is we are going to variate the partial pressure of toluene. Let's say it's 1 bar, just at the beginning, just to begin with the initial guess. The partial pressure of hydrogen, as the problem says, that we need to assume stoichiometric input of the reactants. What we're going to assume pressure. What we are going to assume is that if we see at the reaction, we see that 1 mole of toluene reacts with 3 moles of hydrogen. We are going to assume that for each mole exerts the same amount of pressure. So, for example, if this exerts one bar, the hydrogen would exert 3 bars. If this exerts 2 bars, this exerts 6 bars. So that is one of the assumptions that we need to take in this problem, so we can solve it. So I just said the partial pressure of hydrogen is just 3 times the partial pressure of toluene. So there we have the first condition for this problem. So the second condition of the problem is the equilibrium one. Equilibrium. So for that, let's copy and paste this equation because we're going to use it. So if we see on the second part of the KP equation, it says is the partial pressure of the products raised to its stoichiometric coefficient divided the partial pressure of the reactants raised minus its stoichiometric coefficient. So that is the equation that we're going to use to solving the partial pressure of C. In this case, that would be the cyclohexane. So let's write this equation in relation to our reaction. Let's copy and paste our reaction so we don't forget about it. This reaction is the same one from here. So let's follow this equation. It says that Kp it's equal to the partial pressure of C raised to its stoichiometric coefficient, that in this case is 1, divided P, the partial pressure of A raised minus its stoichiometric coefficient. The stoichiometric coefficient of A is minus 1, so minus times minus is positive. And this would be also divided by the partial pressure of B raised to its stoichiometric coefficient. Wait a second. Yes, raised to its minus its stoichiometric coefficient. The stoichiometric coefficient of hydrogen is minus 3, so it's raised to 3 because minus times minus it's plus. So we have this equation, and as you can see from here, we can solve for PC. And how we do that? We just multiply everything that is divided in this equation to the left hand side, and there we have PC. So PC would be the Kp times the partial pressure of A, that is toluene, times the partial pressure of hydrogen raised to the third power. Okay, and the final condition is the simplest one. It says that the total pressure is the sum the final pressure, we assume the Dalton law. This law says that the total pressure of a system is just the sum of the pressure of its components. So we just say that the total pressure is the sum of the three components. Okay, so now we are ready to start our solver. This would be our objective. So what we are going to do is let's go to data. What we're going to do is that this pressure needs to be 1 bar. That is the only thing that we're going to to specify in our problem, and the cell that we're going to change is the partial pressure of toluene. So let's do that. The objective would be the total pressure, and as the problem says, the total pressure needs to take a value of 1 bar, and the cell that we are going to change is the partial pressure of toluene. Then we solve, and there you have it. Now we have the answer for this problem. This would be, let's see if everything is correct. Yes, everything is correct. Yes. Yes. What did the problem say? Let's read once again. Calculate the equilibrium partial pressures at 600 K and 1 bar, and this would be the partial pressures for this at this temperature. At this temperature, let's remember we have this Kp value, and they asked us to calculate it at 1 bar of total pressure, as here. All these three conditions are fulfilled, and yes, that would be for 600 Kelvin and 1 bar. But the problem also says that we need to calculate this at 500 Kelvin and 50 bar. So we just use the same procedure. I'm just going to copy and paste it. But this time it's not at 500K, but at 600K, but at 500K. And it's at, as we can read here, a 50 bar. 50 bar. The Kp in this case is this one, 74. Let's see. We don't know the initial value of the partial pressure, so let's say it's 1 for now. The partial pressure of hydrogen is 3 times the partial pressure of toluene, so we have that condition. The equilibrium condition of this equation, it's also specified here. We solve for the partial pressure of cyclohexane, and the sum of the total pressure is just the sum of the pressure of each component. So we're going to do exactly the same procedure. We go to solver. We are going to select our objective, would be the total pressure. We're going to give a value of 50 bar as the problem specifies, and the cell that we are going to change is the partial pressure of toluene. And we solve the equation. And yes, also the solver fulfilled this problem. Let me check that everything is correct. Yes, it appears so. So these are the 3 partial pressures for the 3 components at this Kp and at this pressure and temperature. So that would be point C. Let's read 12 points right there. So point D, it says discuss the result. What should be done to increase the efficiency during the process of storage? Why is it useful to think in terms of a catalytic process? Why is the industrial process of recovery easier? What are the limits of technical application? So this type of question is much more a theory question, not a practical one. So you should be able to answer this by yourself. I'm not going to explain it here. This is just a practical guide. So this would conclude our example of today. So a quick recap. As you can see, as you can see, this problem can be solved really fast if you are very organized. The way of how you calculate the Kp, it's by your own. You can use the sum product function that you use several times, as you see, or you can do it by hand, or organize it in a different way. Anyway, just how you feel most comfortable. And yes, this point can be solved really fast if you know exactly what to do. As you can see, I didn't take many time solving the solver problem, the optimization problem, but explaining it, it's another story. So yes, you should decide if you want to solve this type of question in your exam. And yes, that would be everything for today. So if you found this video helpful, please fill down the survey below. It helps me really much in my master leadership class. And that would be all. I wish you success in your upcoming exams.